Professor Bialis here. In this video, we're going to talk about section 4.5, which is systems of equations and problem solving. Again, these are word problems. Now, I will say this. There are some of the word problems in this section that they give you for systems that don't really require systems. So when I'm going through these, some of these I will not present as a system of equations. To me, if you can get away with one equation, why on earth would you introduce a second one? Okay, sometimes you have to. You really can't avoid it. But if we can, I would suggest just stick with one equation at a time. Okay, so I'm going to go through the practice problems as we always do, but I'm going to start with practice 2. Okay, so practice 2 is found on page 285, and it reads, find two numbers whose sum is 30 and whose difference is 6. Find two numbers whose sum is 30 and whose difference is 6. So again, what are we talking about? We're talking about numbers. Number problems typically are translation problems. So again, we have two numbers. Okay, this is where we have our two variables. We can't say a number's x and then another number's x. If they're the same, great, but we can't guarantee that. So that's why we need to introduce an x and then a different number y. Okay, but it says that their sum is 30 and their difference is 6. So if I take two different numbers, their sum is 30 and their difference is 6. And there's your system. When you have two unknowns, you should be searching for two equations. Okay, if you have three unknowns, you need three equations. Okay, otherwise you won't have enough information to get a unique single solution. Okay, so this is your system, solve it. I will never tell you in these problems you must solve with substitution or you must solve with addition method. Use whatever method you prefer. I would suggest though, use that addition method unless you already have a variable by itself and substitution is ready to go. Otherwise, typically I see people have more success with the addition method. So in this case, I'm going to use that addition method because those y's are going to eliminate. Now be careful. I see a lot of people say, oh, x, x, x. They forget to add. There's two x's there. And then we've got 36. I then divide by 2. X is 18. Okay, to get that other number, the y value, I got to plug that in. So I'm going to go here. If x is 18, then I'm left with this. Subtract 18. Y equals 12. Now, usually we would write this as an ordered pair, but since they're just two numbers, we're not looking at an ordered pair necessarily. You can just say that the two numbers are 18 and 12, or 12 and 18. It really doesn't matter. And there we go. Okay, so again, number problems are still just translation. Let's look at another one. Let's go to practice 3. Practice 3 is found on the bottom of page 286, and it reads, a first number is 5 more than a second number. Twice the first number is 2 less than 3 times the second number. Find the numbers. Okay? Now, whenever we're dealing with translation, which that's what we're dealing with again, a sentence gives you an equation. Okay? A phrase gives you an expression, but a sentence gives you an equation. So the first sentence says, a first number is 5 more than a second number. A first number is 5 more than a second number. That's your first equation. So again, a first number is 5 more than a second number. A first number is 5 more than some second number. Say that again and again. Try and write it down. After you write it down, first number is 5 more than second number. Okay? Don't rush through that. That's where most of your focus should be, is writing these equations down. Now I read on. It says twice the first number is 2 less than 3 times the second number. This is getting a little bit more complicated, this equation. So let's go up to that equal sign. Okay, let's just focus on that. Twice the first number is. Twice the first number is. Twice that first number is. Okay, just focus on that. Now we can focus on the rest. 2 less than 3 times the second number. 2 less than 3 times the second. 2 less than 3 times the second. 2 less than 3 times the second one. Remember, less than means you have to flip. So if you're looking at this and you say 2 less than 3 times the second, that's okay, but then you should look at it and say, wait a minute, less than, I have to flip it. So it's 3y, and then lessen it by 2. Okay? And there's your system. Now, in this case, you can rearrange so that everything lines up and use the addition method, but if it was me, I would just use substitution because I already have that x by itself. So I'm going to take this and put it in there. Okay? However, if you're like, no, I just like the addition method better, I don't like substitution, then that's fine. Use that addition method. Use whatever works for you. That's always and will always be the bottom line to it. Okay? So what we get is 2 times 5 plus y equals 3y minus 2. Okay? I distribute and we get this. I then get the variable on one side. And then I add the 2. So y equals 12. And that is one of those answers. Okay, now I need to go back and get that x. Now again, what good thing about substitution is I have an x equals equation. So x equals 5 plus 12. I plugged in that 12 for y. So x equals 17. And then again, they were looking for what are the numbers. The numbers are 12 and 17. Here we go. Again, notice I put the x value second. That doesn't really matter in this case because we're not looking for an ordered pair. We're looking for just 2 numbers. Okay, but if you are worried about getting out of the habit, then write it 17 comma 12. There's no problem with that at all. Okay? Let's look at another one. Okay, so practice 4. Practice 4 is found on page 288, and it reads, "It is considered a premium game when the Red Sox or the Yankees come to Texas to play the Rangers. Admission for one of these games for 3 adults and 3 children under 14 is $75, while admission for 2 adults and 4 children is $62. Then they give you 2 parts to the question. It says, what is the price of an adult's admission and what is the price of the child's admission? There is a third part, but we're going to hold off on that. Okay? So we're talking about going to a baseball game, and they give you 2 different categories of ticket. They give you an adult ticket and a child's ticket. So that's, again, after you read through this thing 2, maybe even 3 times. That's all you should be getting out of it at that point. Let's go back in. It says again, it is considered a premium game when the Red Sox or the Yankees come to Texas to play the Rangers. We were talking about baseball, that's fine. Then it says, admission for one of these games for 3 adults and 3 children under 14 is $75. I'm going to simplify that a little bit. Okay? 3 adults, 3 kids, $75. 3 adults, 3 kids, $75. So we've got 3 adults and 3 children are $75. Okay? That A represents the price for an adult. And then C is the price for a child. Okay? Now let's read on. It then says that 2 adults and 4 children is 62. So 2 adults and 4 children is going to come out to $62. Okay, guys, think about how we bill things. If you have multiple items that you're purchasing, you take that quantity, you times the individual price, that's the total value of what you just purchased. So if, let's say, the adult ticket is $60, if there's 3 adults, 3 times 60 would give you the 180, or whatever price that ends up being. Okay, so that's where these equations are coming from. And remember, we had 2 unknowns. We had the adult ticket price and the child's ticket price. 2 unknowns leads us to 2 equations, okay, or gives us the necessity for 2 equations. Now, we have this system that we can solve. And when we solve that, we're going to find the price of the adult ticket and the price of the child's ticket. Okay, so that will fulfill the 2 questions that they gave us at the end. Now, let's go through this. I would use the elimination method here, okay, or the addition method if you call it that. So I'm going to go after these A's, okay? Now, they specifically said, give me the price of the adult ticket, that's all I want. Then eliminate the C's, because then you're left with A and you can find your answer and be done. But since we have to find both, it really doesn't matter which one you eliminate. So I'm going to go after the A's. So I'm going to eliminate them by turning them both into a 6. That would be a 2 here and a 3 here. But remember, they have to be opposites. So I'm going to put a negative on one of them. Okay? Now what that gives me is a 6A plus 6C equals 150. The negative 6A minus 12C equals negative 186. Okay? The A's cancel out by design. I can cross those off. 6 minus 12 is negative 6. And I have negative 36. Divide by negative 6. And C is 6. Now remember, C stood for the price for a child's ticket. So I know that a child's ticket is $6. Okay? We're not done. They also wanted to know the price for that adult ticket. Okay, so we have to plug in and see what that tells us. So you plug into any one of these 4. Okay, they'll give you the same answer no matter which one you plug into. I'm going to go up here. So I've got 3A plus 3 times 6 for that child's ticket equals 75. Okay? That gives me 3A plus 18 equals 75. I can then subtract 18. So 3A is 57. Okay? And then I divide by 3. And A is 19. So that tells me the adult ticket price is $19. Okay? Now, there is a third part to this. The third part reads, suppose that a special rate of $200 is offered for groups of 20 persons. Should a group of 5 adults and 15 children use the group rate, why or why not? Okay, so again, there's a sale going on, but we need to know if that sale is going to benefit us. Okay, because it's a very specific sale. Okay, it says you have 20 persons, $200. Okay, but for us, we want to bring 5 adults and 15 kids. Okay, so we've got 5 adults and 15 children. Okay, that's 20 people. Would it benefit us to take that deal and just pay $200? Well, to figure that out, we need to use these normal prices and see how much that's going to be. So if I do that, how much are these adults paying? They're paying $19 times 5 adults. How much are the kids paying? They're paying 15 kids each $6. So what does that come out to be? I've got 45, and then I get a 9. So it's $95 for adults. And then the kids are going to cost $90. Okay, what does that come out to? 90 plus 95 gives us 185. So normal ticket price is going to be $185. Should I use that $200 deal that they're giving us? No. When would we use that deal? Why are they even making it if it's cheaper just to do the normal price? What if we had 20 adults? Okay, what if we had 20 times 19? Then we have a pretty darn good deal if we just go with the $200. Okay, so we have to always think about what's happening. Okay, yes, we have a sale, we have a deal. Get these two and you'll save. Sometimes you're not really saving. Okay, so it's just that awareness and that breakdown that can show us what's really going on. Okay, so let's look at another problem. Let's go to practice 5. Okay, practice 5 is found on page 289 toward the bottom. It reads, in 2007, the French train TGV V150 became the fastest conventional rail train in the world. It broke the 1990 record for the next fastest conventional rail train, the French TGV Atlantique. Assume the V150 and the Atlantique left the same station in Paris, with one heading west and one heading east. After 2 hours, they were 2,150 kilometers apart. If the V150 is 75 kilometers per hour faster than the Atlantique, what is the speed of each? Okay, now that's a very long, drawn-out problem. You may have to read this 2 or 3 times to get what they're talking about. Okay, but we have 2 trains, and one used to be the fastest, and now we have one that's a little faster. Okay, so what they mention here are distances, rates, and times. So whenever we have that situation, we want to show 2 scenarios, each with their own distance, rate, and time. Okay, now when I say scenarios, they're like characters in the story. Okay, and in this case we have 2 very separate trains. And those trains were the V150 and that Atlantique. So I have the V150 and the Atlantique. Okay, now distance, rate, and time. Let's see what kind of information they give us. Now we've seen these in the past, and this is not going to be any different. They're going to give us one of those, they're going to describe the other, and then we're going to use those 2 to build the third. This is one of those scenarios where honestly I wouldn't use a system. There's really no need to use a system in this case. Some distance problems will, and I'll show you one of those next. But in this case, this is just a normal distance problem. Okay, so let's see what it says. It says again, the first sentence, in 2007, the French train became the fastest conventional rail train in the world. It broke the 1990 record of the next fastest conventional rail train, the French TGV Atlantique. Those first 2 sentences, honestly, cross out. You don't have to read them again. They're just setting the stage for everything for you. Okay, so we're dealing with 2 different trains. Let's go to the third sentence. It says, assume the V150 and the Atlantique left the same station in Paris, one heading west and one heading east. So what we have is a starting point, one going west, one going east. Okay? Now, after 2 hours, they were 2,150 kilometers apart. Okay? So 2 hours and then 2,150 kilometers apart. When we deal with that distance apart, please realize that that distance is a combination of each of their individual distances. But if they're leaving at the same time and 2 hours pass, then they're each going for 2 hours. Okay, so we can fill in those times. But the distance, let's hold off on that for a second. Then it says that the V150 is 75 kilometers per hour faster than the Atlantique. So the V150 is 75 faster than this. So this, they say nothing about. But this bumps it up by 75. Okay, so they gave us this. They described this. Okay, we are going to use these 2 to build the third. The distance here is rate times time. And distance here is rate times time. There is no need for a system of equations here. There's absolutely no need for that. Okay, what they're having you try and do is make two variables with a distance here and then a different distance. You don't need to do any of that. I would keep it as a single equation. Okay, now remember, those variables that you built on your own are going to be used to build your equation. Now, in this case, are those distances the same? No, but we do have a total distance of this 2,150. Total simply means you add them up, and we get that. Okay? This is our equation. No need for a system. I'm not saying that using a system is wrong or it can never be used, but again, why use two equations when you can get away with one? Okay? So, what we have is a 2r plus 150 plus 2r equals 2150. That's 4r plus 150. All I did was combine like terms there. Then I subtract 150. So 4r equals 2,000. And then I divide by 4. And I have 500. Okay, once I solve the equation, go back to the problem, make sure you answer the question. And again, it said, what was the speed of each train at the very end? So that R, we paired with the Atlantique. So I know the Atlantique is 500 kilometers per hour. That V150, remember, was 75 more than that, so we have 575 kilometers per hour. Okay, some instructors are very picky with how you write your answer. Okay, if they ask you to write out your answer as a complete sentence, then please do so. I'm not saying that's bad, but for me, as long as you specify which is which, I'm happy. Okay? So, let's look at another one. Let's actually go into the exercises, and I want to jump to number 28 in the exercises. We'll come back and finish the practice problems in a second. So again, this is number 28 in the practice problems in the book. That's found on page 296. Okay, now it says, the Jonathan Schultz family took a canoe 10 miles down the Allegheny River in 1.25 hours. After lunch, it took them 4 hours to return. Find the rate of the current. Now I want to do this one because this is a distance problem again, but it will require a system of equations. Okay, so sometimes you can get away without them, but sometimes you need them. So again, this is a distance problem, so we are going to have two scenarios, distance equals rate times time. Okay, so let's dig in again. The Jonathan Schultz family took a canoe 10 miles down the Allegheny River in 1.25 hours. Okay, so they tell you that we went down the river, and then after lunch, it took them 4 hours to return. So if you're going downriver, if you return, you're going upriver. So we've got downriver, and then upriver. Okay. Now again, they very specifically told you that they took a canoe 10 miles down the river in 1.25 hours. So the distance, 10 miles in 1.25 hours. After lunch, the return trip took 4 hours. Okay, now we have to fill in a couple gaps here. If it's a return trip, then that means we have to assume that they literally just turned around and came back where they came from. Okay, went back where they came from. So the distance covered back should still be those 10 miles. But now it's taking them 4 hours to cover that same distance. Okay? Now, this is a little different than what we've seen in the past, because usually they give us one item. Here they gave us two. Okay? However, we are going to have to be a little creative with the rates. We've seen a problem like this back in chapter 2, where we had a rate of current pushing us back or helping us along the way. Here, they don't give us that rate of the current. Okay? Again, in chapter 2, they said like the current is 3 miles per hour or something like that. They don't give that to us here. So we have two unknowns. We have not only the unknown speed of the canoe, but the unknown speed of the current. Okay? Now, those two unknowns are going to combine a certain way to give the overall rate. So what we have is the speed of the boat, and when we're going downriver, we will increase by the speed of the current. Okay? But when we go upriver, that speed of the boat is going to be decreased by the speed of the current. Okay? When we decrease the speed, it takes us longer. Okay? Those two things, we should be able to make sense of all the things that we're writing down when we pull them all together. Okay? So again, look back in chapter 2. I believe it was section 7 when we were dealing with further problem solving. And there is an example like this where we have a current that's given to us. We don't have that here. Okay, now we have two unknowns. That means we need to have two equations. Now those equations are laid out for us in the table. Remember, distance equals rate times time. So this first row, we can say distance equals rate times time. Distance equals rate times time. Okay? Now, at this point, we need to solve this system. If you look at this, the first instinct would probably be, I'm going to distribute. Okay? However, I'm going to show you a little trick on this. If these weren't here, wouldn't that be a very easy system to solve? Because those C's would just cancel immediately. Okay? Let's try and get rid of these numbers without putting them on the variables. When we distribute, remember that's a fancy way of multiplying. So instead of multiplying that out, let's divide the number over. Okay? I'm going to go down here first and divide by 4. Look how nice that right side turns out. And we simplify that to a 5 over 2 equals B minus C. Okay? Now, I want to tweak this a little bit. 1 1/4. I'm going to rewrite that as 5/4. All I do is convert that mixed number into an improper fraction. Now, I don't want to divide by 5/4. Not that that's wrong, but that gets a little complicated. It's what we call a complex fraction then. So what we're going to do instead of dividing by 5/4, remember dividing by a fraction is the same as multiplying by the reciprocal. All of that is gone. We have B plus C. And now what do we have here? Okay, 4 times 10 is 40, divided by 5 is 8. Or you could reduce the 5 and 10 to make it 2. 2 times 4 gives you that 8. And now we have a much simpler system. Okay? Now, what were we looking for? They were asking us for find the rate of the current. Okay? Now, if we leave it as is, those C's go away. Now we find B. But then we have to take that B, plug it back in, and find the C. So if we're looking for the current, keep the current. Get rid of the boat's speed. Now, how do we do that? We just need opposites. So what I'm going to do is I'm going to multiply this equation down here by a -1, which essentially changes all the signs. Again, what I did is I multiplied by a -1, changing those signs. Now that's gone. And I'm left with the variable that I was asked for. So I've got 2C, and then 8 minus 5 halves. Okay? Remember, 8 How many halves are in 8? 8 times 2 is 16. So I have 16 halves minus 5 halves is 11 halves. Okay? I can then divide by 2. But if I have a fraction here, don't divide, multiply by the reciprocal. Instead of dividing by 2, I could also multiply by a half. And we get 11 over 4 is that speed of the current. Okay, and we were talking about miles and hours, so that current is 11 over 4 miles per hour. If you want to write that as 2 3/4 or 2.75, that is perfectly fine. Or you can leave it as that 11/4. It's up to you, whatever you prefer. Okay, I got a little tricky with how I was solving this. You don't have to do that. You could just distribute and then clear fractions and make a match and all that stuff. You can go through all that, but that will require a lot more algebra. If you're not ready for all this, then don't do it. Go through the motions. But if you feel comfortable, start thinking about these things. That doesn't mean you're going to see them every single time, okay, and say I'm always going to do it this way, okay? But if you know 1 out of 4 times you can kind of finesse your way through it, that's worth it. Okay, so start kind of thinking out of the box if you feel ready, but be honest with yourself. Okay, if you're not ready, just stick with the routine and try not to deviate from it. Okay, let's go back to the examples, or the practice problems, I should say. Let's go into practice 6. So practice 6 is found on page 291, and it says, Keith Robinson is a chemistry teacher who needs 1 liter of a solution of 5% hydrochloric acid to carry out an experiment. If he only has a stock solution of 99% hydrochloric acid, how much water, which is 0% acid, and how much stock solution, which is 99%, must he mix to get 1 liter of 5% solution? Round your answer to the nearest hundredth of a liter. Okay? So, in this case, this should sound familiar. We're mixing. When we mix, we draw our boxes. Okay? Now, what we need at the end of this is 1 liter of a 5% acid solution. So at the end, we need 1 liter of 5% solution. But we don't have what we need. All we have is 99% solution. That's stock solution. Okay? Now, what we mix with things to dilute them down, to make them weaker, is typically water. And that's what they're talking about here. Okay? So we are mixing water with that stock solution. The stock is 99%. And water, we are always going to consider a 0% because that is just a diluting agent, okay? So it's just a 0%. Now, if they ever mention like a pure acid, that would be 100%, okay? That's sometimes a thing they give you that doesn't have a number attached to it. So water in these mixture problems would be considered 0. If it's pure something, pure antifreeze, pure acid, you throw 100% in on that, okay? Now, let's dig in a little bit more. So they say that we need the 1 liter of 5%. All we have is 99%. So then it asks, how much stock solution must he mix to get, how much water and stock solution must he mix to get the 5% that he needs? Okay, round your answer to the nearest hundredth of a liter. So really, this is all they give you. Okay. Now, when we saw this in chapter 2, what we did was say, well, I don't know how much of this, but then we took the total minus that variable here. Okay? And then what we did to build our equation was 0 times x plus 0.99 times 1 minus x equals 0.05 times 1. That's how we did it in chapter 2, and that will work here. Okay. However, this throws a lot of people for a loop. Okay. If it's very consistent, you shouldn't have to overthink it, but it sometimes throws a little layer of confusion. So another possibility for this is to use a system. I'm going to show you this because sometimes people prefer it. Okay, I'm going to keep this here just as a reference because I want to show you something in a second. What I sometimes see people do when they want to use a system is they say, I have no idea how much of this I need, and I have no idea how much of this I need. Notice I now introduced another variable. Okay, I didn't define this using that variable. I just said, I have another question mark. I have another variable in there. Now when I do that, I have two variables, I need two equations. Your first equation is going to be just like this one, where we would say 0 times x plus 0.99 times y equals 0.05 times 1. Okay? Now, for the second equation, we are going to use all of these amounts that we have along the bottom. And it would be x plus y equals 1. And now we can solve this. Okay? So again, I personally would suggest just doing it how we were doing in chapter 2. 1 minus x, you're done. Okay? But if this has been kind of throwing you off, then just make it a y and create two equations. Now I want to show you though, when we do this, let's just say we use substitution, okay, just for the sake of discussion here. If I'm using substitution, I need to solve one of these equations for a variable. Let's say I solve this one for y. If I solve that for y, what do I get? Whoops, there should be a plus sign. I would subtract that x, so I have 1 minus x. Does that look familiar? Okay, and then to substitute, I would put this in for y. Okay, so I have 0x plus 0.99 times 1 minus x equals 0.05 times 1. I really spelled that out because I wanted to show you a side-by-side comparison. What we did in chapter 2 jumped us right to this. What we're doing in chapter 4 right now starts us here, and then we still end up in the same spot. Okay, so again, if you want to use a system, go right ahead, but this right here is the reason I usually don't push it, because we had the capability of doing it before. Why not still do it that way? Okay, but again, it is up to you. Do what you are comfortable with. Let's go on from here and solve this. Now the good thing about that 0 is that entire term just zeroes out. So what we get is a 0.99 minus 0.99x equals 0.05. Subtract 0.99. I got negative 0.99x equals negative 0.94. I'm going to divide by a negative 0.99. And it's said to round. So what we get is a negative 0.94 divided by negative 0.99. They said to round to the nearest hundredth. So that would give us a 0.95. Okay? Now that x we placed in the water. Okay? So that means we need 0.95 liters of water. And then y was 1 minus that. 1 minus 0.95 is 0.05 liters of stock solution. And There we go. Okay, or you can say of the 99%, whichever way you want to write it, as long as you're specifying which is which. Okay, the rounding. Make sure if they ask you to round or you ever need to round, you don't round until the very end of the problem. I see a lot of students round in step 1, and by the time you get to step 4, your answer's way off. Okay, so rounding is necessary, but make sure you do it appropriately. Okay, so again, this one, you have an option. You want to do it the way we did it in chapter 2, where it's just one equation, that's fine. Or if you like x and y, then we got to go through that system. Okay, so let's look at another one. So look at practice 7. So practice 7 says, an online only, this is on page 292. It says, an online only electronics firm recently purchased $3,000 worth of new equipment to create shock-proof packaging for its products. The cost of producing one shock-proof package is $2.50, and the firm charges the customer $4.50 for the packaging. Find the number of packages that must be sold for the company to break even. Okay. Now, again, they want you to create a system here, but there's a more fundamental way of thinking about break even. Okay, we don't need to look at two different ideas. Break even simply means when the money going in equals the money going out. Okay, because if you create a business of any kind, typically you have to make an initial investment. You have to buy, you have to rent a place, you need to buy equipment, and you need to buy advertising, all that stuff. That creates a hole. Okay, you're in debt at that point. But then as money starts coming in, you start filling that hole. And as that hole gets filled, you hit that point where you've paid off all that initial cost. And then after that, you start turning a profit. That's the break-even point, where that hole gets filled. Okay, so this is a break-even problem, and it'll say that in the problem. And that simply means money in equals money out. Nothing more to it than that. Okay, so now let's figure out where the money in is and where the money out is. So it says, an online-only electronics firm recently purchased $3,000 worth of new equipment to create shock-proof packaging. So we purchased $3,000 as the business owner. That's a money out. Okay, so money out, I made a one-time purchase of $3,000. Okay, after that, it says the cost of producing one of these packages is $2.50. Okay, if I'm making something, I need to buy materials. I need to pay for the electricity. I need to pay for whatever, you know, the labor cost, all that stuff. So to produce one of these, it's going to cost me $2.50. However, it's not just a flat $2.50. It's $2.50 per unit. So I'm going to multiply that by X. And X is number of units. Okay? Then you read on and it says that when I sell these things, I'm actually going to sell it for $4.50. Okay? So that is money coming in. But it's not just $4.50. It's $4.50 each time I sell a unit. Okay? So, money coming in is when I sell things. Money out was the cost to make it and the initial cost for all that machinery. This now can be solved. So watch for this, what happens with this first step. If I get the variable on one side, what's 450 minus 250? It's just 2. Think about that. If it cost me $2.50, I'm selling it for $4.50. How much am I making every time? I'm making $2. Okay? So every time I make and sell, I make $2. That $2 is what I'm going to use to fill that $3,000 hole that I started with. And then I divide by 2. and I need to sell 1,500 of these things. You can call them units, you can call them the packaging, whatever it is, before I break even. Okay? Now, is that a good business model? We don't know. Because we don't know if, is this going to take us 5 years to sell? Are we never expecting to sell that much? Or is that going to take us a week to sell? Okay, that's where, if you're going into a business administration or any kind of field like that, that's when you analyze, what should we expect? When should we expect this to be hit? Okay, is that a good investment to start this business or not? Okay, so break even, money in equals money out. Let's do one last one. This is practice 8. Practice 8 is found on page 294. It reads, the measure of the largest angle of a triangle is 40 degrees more than the measure of the smallest angle, and the measure of the remaining angle is 20 more than the measure of the smallest angle. Find the measure of each angle. Okay, so we are talking about a triangle, and we've got 3 angles, and they're describing those 3 angles to us. Okay, so if it helps to draw a triangle, or they talk about largest angle and a third remaining angle and all that. So we've got a triangle here. Let's see what it says. Let's go in and get a little bit more detailed information. The measure of the largest angle of a triangle is 40 more than the measure of the smallest angle. So that smallest angle they mention, but they say nothing about. So if I go with my smallest, largest, and then let's call this one the middle one. Okay, so again, it says the largest angle is 40 more than the measure of the smallest. I know nothing about my smallest angle, but my largest is 40, more than the smallest. Okay, then I read on. And the measure of the remaining angle is 20 more than the measure of the smallest. Okay, so the remaining angle is 20 more than the measure of the smallest. Okay, find the measure of each angle. So, what do we do with that? Now, in this case, we have 3 angles, all referencing the smallest angle. Okay, so notice how we were able to write and describe each of these using the same variable. Do we need a system with that? In this case, no. Okay, what do we know about all 3 angles of a triangle? They have to add up to 180. So I have x plus 20 plus x plus 40 equals 180. And that gives me 3x plus 60 equals 180. I can subtract 60 to get 3x equals 120, and then divide by 3. And I get x equals 40. Okay? That x was my smallest angle. That next one is 20 more. And the largest is 40 more. 40 more than this. So that gives me 80. And those are my 3 angles of the triangle. So again, could we have written this as, okay, this is x, this is y, this is z? You can. But then you're creating a problem that doesn't need to be there. You're creating variables that don't need to be there. Okay? That's a perfectly fine way of doing it, but it's just more complex. Okay, so again, if you can, try to do this with one variable, but don't necessarily force it. If you have to rack your brain to figure out how to just get one variable, then just do the system. But in a lot of these, you can very easily avoid it because it's going about it the same way we did it back in chapter 2. Okay, so we went over a lot in this section, but I want you to take your time with it. Take it one problem at a time, one situation at a time. trust yourself, trust the process, and you'll do great. Okay, as always, if you have any questions, let me know. Work hard, and I'll see you next time.